Today we are going to discuss on our stabilization strategy, primarily focus on managing the use of low cost material. This material include nut coke, which consists of a smaller coke fraction used to substitute larger, more expensive coke. We also utilize ferrous fines such as fine sinter or low grade ores charged directly to reduce reprocessing cost. Finally, we used injected coal (PCI) and alternatives to replace expensive prime coke in the stack. The area of intervention cover stabilization technique, which are based on rule-based operation and operational guides. For nutcoke charging, the goal is to charge all available screen nutcoke without losing process efficiency. Assuming satisfactory coke quality, nutcoke is typically mixed within the ore layer to improve chemical reaction kinetics. For a radial distribution, we restrict nutcoke charging to the blast furnace wall area up to maximum of 40% of blast furnace radius to ensure high permeability is maintained in the central region. Extending nutcoke distribution too far towards the blast furnace center must be avoided as this led to detrimental effect in operational tests. We modify screen nutcoke rates based on coke cold strength measured by Micom 10 value. Decreasing the maximum size of nutcoke, for example, from 30 millimeter to 25 millimeter, improved permeability by increasing the portion of coarse coke. We use reducing agent like pulverized coal injection (PCI), oil, gas, or compatible waste to replace part of coke charge at the top. When PCI injection rates are high, above 160 per ton of hot metal, maintaining nut coke level between 60 and 80 kg per ton of hot metal provided the best permeability and low thermal losses. Alkali control is necessary because components like zinc and lead act as a poison to the blast furnace, often leading to restriction on recycling material containing high concentration. Operator must monitor the alkali load such as K2O as low value in the slag may indicate a growing alkali load inside the blast furnace, which stresses the coke and negatively affect permeability. Under strategy 2, the maximizing ferrous fines utilization, the rate of total fines plus low grade ore shall not exceed 8% of the ferrous burden if high permeability is required. High permeability resistance coefficient or PRC result when low coke harmonic mean size occurs regardless of fine level, but when coke HMS is high, excessive fines cause PRC to rise. High rate of ferrous fines defined as over 3% of ferrous burden should only be used when blast furnace operation is good and stable. A stable operation requires a low heat flux as well to maximize the use of these fines. For coke quality, the Micom 10 values, which is an indicator of cold strength, must be below 5.8%. High Micom 10 coke, which signals poor quality, lead to high heat flux, which should be avoided when using high fines level. The calculated composite coke harmonic mean size HMS after direct reduction shall be above 42 millimeter. Large coke pieces or particles, we can say high HMS, support suitable gas flow and hearth drainage, enabling better use of fines. Regarding sinter quality, the FU content of the char sinter shall be above 7.5%. Higher sinter FU is beneficial, likely because it improves the sinter softening and melting properties, stabilizing gas distribution. For sinter fines quality, if the percentage of fines less than 5 millimeters in the center exceed 4%, operators should consider temporarily removing ferrous fines from the burden. Ferrous fines utilization should be suspended if the sinter plant is out of action and a stockpiled sinter, which is prone to degradation, is being used, because this material can exacerbate process upset if the blast furnace condition is poor. Radial burden distribution control uses a model to constantly visualize the arrangement of coke and ore layers to manage gas flow pattern in the shaft. The optimal charging surface profile must be maintained where wall center height differences are between 0.8 meter and 1.4 meter, achieved by adjusting the rotating chute inclination. Thermal and gas flow monitoring require continuously monitoring key performance indicator to recognize abnormal working condition. A high central gas flow, indicated by large differences between center and average above burden temperature, support better blast furnace permeability. Rule-based operation system automate detection and suggestion for stabilization, protecting against shaft and hearth wear. The software provides warning if shaft wall heat losses trend towards damaging levels, prompting operators to stabilize the process. Hearth drainage supervision is crucial, especially when inferior raw material impact liquid flow. High hearth temperature and long slack flow times indicate poor drainage, and recommended actions include charging more ore to the center region to increase deadman drainage. Finally, dynamic modeling employs advanced prediction tools such as neural network and fuzzy models to forecast blast furnace parameters like productivity, heat flux, and gas utilization based on raw material inputs, helping maintain consistency in the efficiency. Prediction analysis identify input combinations such as specific PCI and nut coke rates that lead to optimum blast furnace working condition. Stabilization of the blast furnace provides three key areas of benefits. First, we achieve economic advantage. This is due to the increased use of low cost material, ferrous fines, nut coke, and injected agent to substitute more expensive prime coke and iron ore. Second, we realize enhanced performance shown by the improved blast furnace permeability and gas utilization, which translate to potentially reduce overall consumption of reducing agents and stabilize hot metal quality. Third, stabilization delivers operational resilience. The scientific rules and the modeling tools reduce the likelihood of burden slips, uneven descent, and refractory damages caused by high thermal flux or poor drainage associated with unstable operation or low quality input. This also grants increased flexibility, extending the acceptable operational range for key raw material parameter when supplies fluctuate.